This formula right here is called the Wien Displacement law, and Wien it's a German name, so it's spelled like that. And basically the idea here is that the hotter a star is, the bigger T is, and this is of course in kelvins, right? The smaller the wavelength that a star puts out, right? So a hot star puts out a small wavelength, right? And this is the peak of the black body radiation, right? Small stars or hot stars tend to put out very small wavelengths, right? And cooler stars put out long wavelengths, right? Now, if you remember what color means, short wavelengths are like blue. Blue light is short wavelength, right? So hot stars are blue in color, right? And cooler stars are actually red. So it's kind of a reverse of the normal color code that we're using. This is just a constant, that 2.9 times 10 to the minus third, and those are the units that you need to have to make it equal that. Although they didn't bother to put the units on it in the data packet. Here's a little diagram I took from my chemistry book, or my astronomy book that when I took astronomy in college, and I just scanned this out of there, obviously. But these are black body curves. That's what these things are. And there's for 273 kelvins. Then if it's hotter, not only is there, does the peak of the black body, which is right there, not only does it shift to a shorter wavelength when it gets hotter, but it also gets, the whole area under here gets bigger, so they also get brighter. There's the peak of the black body at 1,000 kelvins, and at 2,000 it's there, and at 4,000 it's here, and it's a beautiful linear relationship. This is massively complex. It involves quantum mechanics and all this stuff, right? And Planck and things like that. This is the black body curve of black body radiation, which is the radiation hot objects give off. But the peak follows this beautiful straight line, right? And there's our formula for it, right? Okay, so let's try this. Let's do this. You've got this in your notes. So a star has a surface temperature of 5,787 kelvins. What's the peak of its black body curve, right? So lambda max is 2.90 times 10 to the minus third, and that's meters times kelvins, and then it's divided by 5,787 kelvins, and of course, kelvins goes the way of the bison, and so 2.9 e minus 3 divided by 5,787, and I'm getting 5.01 times 10 to the minus 7th meters, which, if you remember, is 501 nanometers, right? Now remember, the visible spectrum is from 400 nanometers. That would be like blue light, the highest end frequency, right, to about, 700 nanometers. So whatever this star is, it's putting out a nice light that's right in the middle of the visible spectrum. Not smack dab, but pretty much, right? It's going to be pretty much a white light. So it's got to be somewhat like the sun. I'm going to do another example. It's not on your sheet, but that's okay. If you want another example, I'll do another example for you. Okay. A star has a lambda max of 940 nanometers, right? Well, that's pretty big, so that's going to be a lot cooler than our sun, right? Because that's a bigger wavelength. So lambda is, of course, 2.90 times 10 to the minus third meter kelvins over T. So T is going to be, and that's the way all these formulas are like, right? 2.90, 90 times 10 to the minus third meter kelvins divided by the wavelength, right? So that's 940 e to the minus 9, because it's nanometers, right? So 2.9 e to the minus 9, 2.9 e to the minus 3 divided by 940 e to the minus 9. And that's 3,085.1 kelvins, but we have 2 sig figs, so we have to say 3,100 kelvins. Thank you for watching this video and being mindful of the blue pen.